Revisewise programs is about science. It covers changing materials, separating materials, electricity, forces and measurement, light, sound, earth and beyond. The starting time of each program is shown on the menu, so they can be found using the clock in the top right-hand corner of the screen. First, changing materials. In these programs and in our books, audio tapes and on the internet, we're helping you with your Key Stage 2 science tests. This time we're looking at changing materials. Here's a test question about changing materials. Could you read it for us?
The children have been finding out about materials. Which of these materials will dissolve in water? Tick 2 boxes. Then it says wax, sugar, chalk, salt, clay and sand.
OK, well this question is about dissolving. So let's remind ourselves what dissolving is.
Joan, can you think, what does the word dissolve mean?
Sort of disintegrate.
Disintegrate, that's another super word. So what is it that's disintegrating then if we're looking at this situation? If we imagine that's a cup of tea.
The sugar.
The sugar's disintegrating. To dissolve something, and you've already given me the description of what that means, and I'll just pop this up beside it. When a substance dissolves in water, it breaks up and spreads into the water.
So, any ideas?
Of course. I forgot, but sugar dissolves.
Yep, that's right. So you've got one answer. Now let's carry on and see if there are any more.
Colin, would you like to take the tub, and could you put in 1 teaspoon of salt, please? Try and make it as level as possible if you can. That's great. Now, Nikki, you're going to add some water, just enough to cover the base of that tub. Can you see it dissolving?
Yeah.
So, what else dissolves?
Salt.
Very good. Now tick the boxes to get the marks. Some materials dissolve, but others don't. The children investigated.
Now, they're all very much everyday substances that you would come across perhaps in your house or even in school. We've got chalk, washing soda, bicarbonate of soda, baking powder, sand. Okay, we also have talcum powder, Epsom salts, which you may have heard of, and glucose. Okay, so these are our 8 substances which we're going to test for solubility or insolubility.
And what did they find out?
There's no residue, there's no grain, any kind of grains in the bottom. They're all completely dissolved away. What substances are they? Colin, can you read them out?
Bicarbonate of soda, washing soda, Epsom salts and glucose.
Right, so these 4 substances are what we would call soluble substances. The insoluble substances, well, you can see the difference. It's really quite drastic, isn't it?
So, the children found out that the talcum powder, the chalk, the baking powder and the sand were all insoluble substances. They didn't dissolve. Now, there's something else worth thinking about. Once something has dissolved and it's in a solution, do you think there's any way of getting it back? Let's have a look.
Right. Starting quite quickly because the ring was nice and warm before we came out. Okay, what's happening to the solution? Colin?
To boil.
It's boiling, it is, it's boiling away. How do we know that it's definitely boiling?
Because there's bubbles coming out of the water.
Right, the water is bubbling away quite furiously there, so the ring's been nice and hot when we've put the solution on. Can anyone predict what they think we might see. What do you think we might be left with, Vicky, or what might form?
Some salt.
And do you think it will be like the salt coming out of the salt cellar that you would have on your table?
No, it would be different.
Now, this is exceptionally hot, so I don't want anyone to touch it. Can you see that? We'll take it over to the bench over here and have a closer look at it.
You may not have done all that boiling in your school, but you probably did something very similar. For example, you may have left a saucer full of salty water out on the windowsill or on a radiator. Well, I did the experiment myself, and here's my saucer now. The water evaporated and left the salt behind. So what do you think this is telling us?
Well, maybe when you dissolve something, you can get it back.
Exactly. Dissolving is a bit special, isn't it? When a soluble material dissolves, it looks as if it's disappeared, but it hasn't really. If you've dissolved salt and sugar, for example, you'll still be able to taste it. But more importantly, you can get back the material that you've dissolved when the water evaporates. I tell you what, there's something you don't need to know about just yet, but it might help you to understand dissolving. Just have a look.
To understand what's happening, you need to know exactly what's going on when something dissolves. You need to look at it really closely. Imagine you had an eye more powerful than the most powerful microscope. What might you see when sugar dissolves in water? The water itself is made up of many tiny particles, all moving around randomly inside the container. The sugar is made up of bundles of sugar particles called crystals. When the sugar dissolves in the water, the bundles of particles which make up the crystals break up. They become completely mixed with the particles of water. All the particles move around freely and the whole solution behaves as a liquid, so you can't see the sugar. The sugar particles move around in the gaps between the water particles. There's room for them to slip in between. This means the volume of the solution does not increase that much when sugar is added. So you can add more than you think before the glass overflows.
Clever, eh? Do you know what it's called? A reaction which can be reversed?
Well, give us a clue.
Okay, well, you might have talked about it when you learned about solids, liquids and gases. When something changes from one form to another, from solid to liquid, for example, it can go back to its original form. We say that the change is...
Reversible.
Exactly. Now, there are two types of change. Reversible changes, we've just talked about. The other sort are those in which the materials can't go back to their original form, and they're called...
Irreversible.
Yep, now if you think about it, not all things can change and then change back to exactly the way they were before. I'm sure there's a question about this somewhere in the paper. Yeah, read that one.
Diane put a wax candle on some scales. The teacher lit the candle and left it to burn. Diane noticed a liquid around the bottom of the wick. What is this liquid? That's easy, it's wax.
Okay, and what's the name of the process when a solid turns into a liquid?
It goes soft.
Now that's not scientific, is it? We have to be exact and use the proper scientific words.
The proper word for it goes soft is... it melts.
Excellent. Now on to the next part of the question.
Diane measured the mass of the candle every 30 minutes. Her results are shown on this graph. What happened to the mass of the candle while it was burning? That's a bit difficult.
Let's have a look at Diane's graph in the question. It says Diane constructed this graph with her results. What she did was to measure the mass of the candle every 30 minutes. Each time she took a measurement, she drew a cross on the graph to represent the result, and then she linked all the crosses. At 0 minutes, the mass of the candle was 16 grams. Then at 30 minutes, it was 14 grams. So we can see that the longer the candle burned, the smaller its mass became. Now you might have thought the answer was that the candle got shorter. Well, of course, it did. But this is not the answer to the question. Let's have a look at the question again. The question asked what happened to the mass of the candle. A mass can't get shorter, only smaller. Don't forget, science is about using the exact words.
So the proper answer was that the mass got smaller?
Exactly. Now write it down.
Here's another part to this question. Gareth said, when the candle wax burns, the change can be reversed. Diane did not agree with him. She said that the change is irreversible. Explain why Diane is correct. I don't get this. I mean, at the beginning of the question, I said that the liquid at the bottom of the lit candle was melted wax.
Yep, and you were right.
But melting is when a solid turns into a liquid, and this change is reversible.
Yep, you're still right.
So why did they say that Diane is correct when she says that when the candle wax burns, the change is irreversible?
OK, I think we need to sort this out really carefully. Look at this film and we'll see exactly what happens when a candle burns. When a candle is alight, two things happen. The wax changes in two different ways. The first change we know about. When the solid wax gets hot, some of it melts and turns into liquid wax. This drips down the side of the candle. As it moves away from the heat of the flame, it cools down and becomes solid again. Solid to liquid, liquid to solid. The wax may be a different shape, but it's always the same stuff, wax. So melting is a reversible change. But there's another type of change that happens to the wax. Many people think that when a candle burns, it's just the stringy wick in the middle that burns, but it isn't. If I hold a burnt-out match in the flame, it doesn't burn. But if I dip it into some melted wax, it burns. So it must be the wax in the candle that's burning. When wax burns, it changes into new stuff. A chemical change happens and we can't get that wax back. It's a different sort of change and it's called an irreversible change. I mean, have you ever seen anything which burned coming back? Never. Burning is an irreversible change.
I get it. When the wax melts, it's the same stuff, just in a different form. But when it burns, it changes into something different. It's not wax anymore.
That's right.
But there's one thing puzzling me. You said that when the candle burns, it changes into something else. So, where are these new materials? Why can't I see them?
Good question. When wax burns, it changes into gases, which we can't see, and they just drift away into the air, which is also a gas, of course.
So that's why the mass of the candle gets smaller when it burns.
That's right. There are often questions on the test papers about reversible changes, like melting and dissolving, and irreversible changes, like burning or baking. So, now do you think you'll be able to answer the question? Why is Diane correct when she says that when the candle wax burns, the change is irreversible?
OK, Diane is correct. The change is irreversible because a chemical change happens when something's burned. We can't get back the things we've burned.
Exactly. One last thing, write it down. Time to put our keywords on the memory map. First, we talked about dissolving. Some materials, like sugar and salt, dissolve. Some materials, like sand or chalk, don't. We call materials that dissolve soluble, and materials that don't dissolve insoluble. Then we talked about reversible and irreversible changes. Examples of reversible changes are dissolving, melting, and any change of state. Examples of irreversible changes are burning and baking. Now you and your teacher can go over some of these things at school. Don't forget, you can always wind the tape back and look at bits of the programme again. There are also our books, audio tapes and interactive Revisewise website to help you make the most of what you know when you're preparing for your test. So, we'll let you get on with your test and you get on with your revision. The next programme is about separating materials. In each of these programmes, as well as in our books, audio tapes and on the internet, we're going to look at all the bits of science that you might find tricky. This time we're looking at separating materials. So, what's the problem?
I'm stuck on this question.
Okay, well read it out then.
The children grind up some green sugar-coated chocolate sweets. They end up with a mixture of powder and some larger pieces. Which method should be used to separate the largest piece of sweet from this mixture? Tick one box. Sieving, evaporating, filtering and dissolving.
Okay.
Well, how am I supposed to know? I've never done this experiment before. I thought this test was about things that we've studied in class.
Yes, you're right. You might not have done exactly the same experiment in class, but that doesn't mean you can't answer the question. Remember, the test is not there to trick you, so you must have done something similar in class. In fact, this question is all about separating materials. Let's get the science team to refresh our memory. In this cup are sand, beans and paper clips which need to be separated.
How are we going to separate these different sized solids without touching them?
First, we can use this magnet and take the paper clips out.
Yes, you're right, but it will only work if these paper clips are made out of magnetic metals such as iron or steel.
Let's try.
It works.
So,
I don't see what you mean. In my question, there's no magnetic metals like iron or steel. It's about chocolate.
okay, well, let's keep looking.
On this piece of paper, I've written what we have done. To separate two different sized beans, we are using sieving. Here I have written the scientific principle that we have to remember. To separate the two different sized solids, we are using sieving.
In the test, we might not be asked about separating two types of beans, but if we know we use sieving to separate different sized solids, then we can answer any questions about separating different sized solids.
So, we use sieving to separate different size solids. These can be anything really, different size beans, beans and sand, different size pebbles, anything. Do you get it?
Yeah, it's not about beans and sand. It's not about pebbles. It's about separating large pieces of sweet from smaller pieces of sweet, which form the powder.
So what's the answer?
Well, I have to choose between sieving, evaporating, filtering and dissolving. So, it's about separating different sized solids. So we should use sieving.
Excellent. Now, tick the box to get the mark. Well done. Now, I wonder, if you had to separate solid bits from a liquid, what would you use?
You can separate solid bits from a liquid in a lot of different ways. If the solid bits are quite big, you use sieving. For example, you sieve to separate pasta from water.
If the solid bits are very small, you will have to filter the mixture. Here I have some sand and water. The grains of sand are very small, so therefore I will filter the mixture.
A filter paper works like a sieve. It has tiny holes which can let the liquid through, but not the solid bits. They're too big to get through the holes. Sometimes, if you use paper that has bigger holes than the size of the solid bits, it won't separate them from the liquid. For example, if you try to filter a mixture of flour and water with a paper towel, the mixture will still be cloudy, which means that there's still some flour in the water. The paper towel has holes that are bigger than the bits of flour, so some bits of flour can get through. Now, if you use a filter paper with tinier holes, the mixture is much clearer. Only tinier bits of flour manage to go through. So, we use sieving for separating solids of different sizes, or for solids and liquids if the bits of solid are big enough. And we use filtering to separate small bits of solid and liquid. That's easy enough. Lots of test questions have more than one part to them, so you must remember to do all the parts and you'll get a mark for each of them. So what's the next part of your question?
They add the mixture of powder and small pieces to the water in the jar and stir. They leave the mixture to stand for 2 hours. Colour comes from the mixture. The liquid in the jar turns green. What process made the liquid turn green? What do they mean by process?
Okay, well, a process is something that makes a change happen, like evaporating, melting, freezing, boiling, or condensing. And don't forget, if you're stuck, to look back at the beginning of the question and you might get important information. Look here, the important information you need is right at the beginning of the question. The children grind up some green, sugar-coated chocolate sweets.
Oh, I get it. It's the sugar coating that was green. So if the liquid turns green, it means that all the green sugar coating has come off the sweet.
Exactly, and what's it done?
It's dissolved in the water.
Brilliant. Do you remember about dissolving? When you mix sugar in water, it dissolves. Here the sugar is green, so when it dissolves in the water, it looks as if the water went green. So the children in the question ground up the chocolate sweets, added some water to the mixture, the sugar dissolved, and...
After 2 hours, there are still some small brown pieces left in the green liquid. Which method should be used to separate these brown pieces from the green liquid? Tick one box. Condensing, filtering, evaporating and dissolving. I know the answer to that. To separate small solids from a liquid, we use filtering.
Cool, tick the box. OK, now, is there another part to this question?
The separated green liquid is heated gently on a radiator until only a green solid is left in the bottom of the dish. Explain what has happened to the water. I know. The radiator heated up the solution and the water went into the air. That's why it's not in the dish anymore.
Explain what you mean by went into the air.
Well, I suppose water turned into water vapour.
So you're saying that the liquid water turned into a
gas?
Yes, and what's the scientific word to say that a liquid has turned into a gas?
We say it's evaporated.
Brilliant, you're getting to be really good at this. Let's just check if there's another part to the question. Questions in the science papers are often in lots of parts.
How does the time taken for the mixture to dry depend on the temperature of the radiator? Well, it has that word depend in it, and whenever it has the word depend in a sentence, it wants me to think of the relationship between the two things.
OK, so what might the two things be? Read the question again.
How does the time taken for the mixture to dry depend on the temperature of the radiator? Well, they want me to find the link between the time taken to dry and the temperature.
OK, any ideas?
I know that the more you heat it, the quicker the water will evaporate.
Excellent. Now, what will your answer be?
Oh, I'd say the hotter the radiator, the quicker the mixture dries.
Excellent. Now, you're going to get all the marks for that answer, but actually there was another answer you could have given me which would have been just as good. Can you think what it might be?
Another link between the time to dry and the temperature?
Yep.
Well, I suppose I could say it the other way around. The colder the temperature, the longer it takes to dry.
Brilliant. Let's join the science team to help you to remember what happened in this question.
With my class, we did this exercise to remember what happens when some things dissolve and others don't. We're like the water, the green sugar, and the chocolate. First, the bits of chocolate and sugar got mixed with the water. Then they were being stirred with a big spoon. We knew we all had to mix up together and keep moving around each other. The spoon stopped stirring. Now, all the chocolate bits separated away from the others, they were sinking to the bottom of the beaker. They didn't dissolve. The green sugar and the water stayed mixed because the sugar had dissolved in the water.
In came the filter paper. The mixture was poured through the filter paper. The large bits of chocolate got stuck. They couldn't get through. Then the water and the dissolved green sugar were left on the radiator. The radiator gave off heat, so as the water got hotter, it evaporated into the air. This left the green sugar behind.
Acting out what's happening in a scientific process is a really good way to remember it. So have a go yourself, but check with your teacher that what you're doing is scientifically correct. And now a question for you all. How can you separate a mixture of salt and sand? Have you got an answer? What about you? Now think about the different properties of salt and sand. What does one do that the other doesn't?
Salt dissolves and sand doesn't.
Excellent. Now how could you use those properties to separate them?
Well, I'll add water to the mixture and the salt will dissolve and the sand won't. Then I use filtering to separate the sand from the salty water. I'll place my beaker on the windowsill and the water will evaporate and the salt will be on its own.
Excellent. Ways like these of separating different materials are used all the time in everyday life. Have a look at this.
This is the Great Salt Lake in Utah. And surprise, surprise, it contains lots of salt. Local industry takes full advantage. A section of the lake has been divided into a huge patchwork of ponds, all very shallow. Salt water from the lake is pumped into the ponds down a canal. The pump itself is encrusted with salticles. As the drops of water evaporate, they leave behind tiny amounts of salt, which build up over time. The water is pumped into these huge ponds and left for many months. The sun heats it up, and the water evaporates, leaving behind salt crystals.
So now it's time to check what keywords we've got to put in the memory bank. We looked at different ways of separating things using magnets, sieving, filtering, and evaporating. We use magnets to separate magnetic materials like iron or steel from non-magnetic materials. We use sieving to separate two solids of different sizes or to separate solids that don't dissolve from liquids. But remember, the solid bits have to be bigger than the holes of the sieve. When the solid bits are very small, we use filtering to separate them from a liquid. We use evaporating to separate a substance that has been dissolved in water from the water. You can combine the different methods to separate a mixture of several things. To separate a material that dissolves from a material that doesn't dissolve of similar size, you add water to dissolve the material that will dissolve, then you filter out the material that won't dissolve, and finally you evaporate the water. And that leaves you with the material that dissolves. Now, you and your teacher can go over some of these things at school, and don't forget you can always wind the tape back and look at bits of the programme again. There are also our books, audio tapes, and our interactive Revisewise website to help you make the most of what you know when you're preparing for your test. So, we'll let you get on with your test, and you get on with your revision. The next programme is about electricity. programmes and in our books, audio tapes and on the internet, we're helping you with your Key Stage 2 science tests. This time we're looking at electricity. Can you find us a question about electricity?
Yeah, here's one. Two children made a model fairground ride. They connected a battery to an electric motor to make the model turn. The motor is not working. What is wrong with this circuit? I don't know. I've never used a motor in my circuit before. We've only used bulbs in our circuit.
OK, well, let's have a look at a few circuits and you'll be able to answer this question in no time. Here's 3 simple circuits. They are different, but each circuit has a battery, a switch, and a component that does something. Let's see what each one does. If we close this switch and make a complete circuit,
the bulb lights up.
If we close this switch and make another complete circuit,
the buzzer buzzes.
And if we make the last one a complete circuit,
the propeller spins round really fast.
That's right. And the thing that makes the propellers spin is called a motor. Now, let's look at the batteries again. Do they look the same?
No, they're not the same. One of them has 2 metal bits sticking from the top of it, and the other ones haven't.
That's right. I've got 2 of the same kind of batteries for you to have a closer look at here. Now, do you notice anything else?
Well, they both have plus and minus signs written on them.
Yeah, you're right. The plus and minus signs are there to let you know where the terminals are. The terminals are where you have to link the battery with the circuit. So on this battery, they're here and here. And on this battery?
Here and here.
That's it. On this type of battery, the top is one terminal and the bottom is the other terminal. And when you put 2 or more batteries together, you have to make sure that they're the right way round, with the opposite terminals together, the plus next to the minus. You can't put 2 pluses together or 2 minuses next to each other, or it won't work. Now, let's go back to our 3 circuits. In this circuit, the electric current flowed through the buzzer and made it work. The current went in and out of the buzzer through these wires. In this circuit, the electric current flowed through the motor and made it work. The current went in and out of the motor through these metal prongs. What about this circuit? Where do you think the current went into the bulb and where did it come out?
I'm not sure.
Well, it depends which sort of bulb it is. Here's a big bulb, like the ones you have at home. Now, the current goes in here and comes out of here. And in a small bulb, the current goes in here and comes out here, or goes in here and comes out here, depending on which way it's connected to the battery. So, now that you know where the current goes in and out of the light bulb, see if you can make this bulb light up using this battery and no wires.
Well, I know that it has to start at one of the terminals and go through the bottom of the bulb, so I have to make it touch like this. Then it goes through the bulb and out the metal edge at the side there. Then I have to make it touch the other terminal. Hey, it worked!
Let's look again at the 3 circuits. In each case, we had to close the switch to make a complete circuit. Because the circuit is complete, the electric current can flow from one terminal of the battery to the other through the light and the switch. Because the circuit is complete, the electric current can flow from one terminal of the battery to the other through the motor and the switch. Because the circuit is complete, the electric current can flow from one terminal of the battery to the other through the buzzer and the switch. Now let's look at some circuits that do not work. See if you can spot what the problems are. The bulb is not connected properly to the battery. For the current to be able to go through the bulb, we need to put another wire like this. There is a break in the circuit. For the circuit to be complete, both battery terminals need to be connected. The wires are connected to the same terminal on the battery. For the current to go through, both terminals need to be connected. There's a break in the circuit. The switch is open. For the current to pass through, the circuit needs to be complete. So, now, would you be able to answer the question? What's wrong with this circuit?
Well, the motor's not working because both the wires are connected to the plus terminal of the battery.
Great! At school, you might use batteries where the terminals are in a different place from the ones in the question, but don't let this confuse you. Always look for the plus and minus signs on the diagrams to know where the terminals are. Now, do you think electric current flows through any material? Sarah from the Experimenter wanted to find out.
I wanted to find out more about which materials let electricity travel through them and which ones didn't. So, I got a battery and made a circuit. Okay, let's see if I got this right. Okay. I think that if I touch these two wires together, then it should complete the whole circuit. The electricity will run out of this end of the battery, along the wire, into the buzzer, making it buzz, out of the buzzer again, back into the wire, round back into the other end of the battery. Let's see if it happens. Yes! My circuit works. Okay, now for the experiment. Instead of touching the ends of the wire together, I was going to touch them to the ends of something else. If electricity passed through it, it would complete the circuit and make the buzzer buzz. It did when I used a fork, so I knew that the fork conducted electricity. So, fork does conduct. I tried a rubber band next. I predicted that it wouldn't conduct electricity. I was right. I predicted the same about a wooden ruler. I was right again. Wood didn't conduct electricity. Next, I tried a copper bracelet. I predicted that electricity would pass along it. And it did. Copper did conduct electricity. I tried a 2p coin as well. And that conducted electricity too. Then I got a pencil. It didn't conduct electricity when I tried the wooden part, so I thought I'd test the middle bit of the pencil. This time, it did buzz the buzzer, only not quite as loudly as the others had. Okay, let's just see if I've got this right. The fork, the copper bracelet, the 2p coin and the middle bit of the pencil do conduct, and the rubber band, the wooden ruler and the pencil wood don't conduct.
Now, Sarah found that the rubber and wood were not conductors. Do you know of any other material which is not a conductor?
Yes, plastic. And I suppose there are others like stone and wool.
Very good. And we call materials which are not electrical conductors electrical insulators. When you're working with circuits, it's really helpful to draw diagrams that show clearly what is happening.
When you first see a circuit diagram, it looks rather like a map with lines and symbols. All these boxes, circles and squiggles each represent a different electrical device. The lines represent the wires that connect them. In the 19th century, when scientists were first learning about electricity, they wanted others to know about their work, and the easiest way to describe what they were doing was to draw it. This is one of the first modern circuit diagrams, drawn in 1878 by Thomas Edison. It's of his latest invention, the incandescent light bulb. By now, scientists were using symbols for the electrical equipment involved. His drawings were logical. The circuit consisted of 2 wires from a battery that connected to a bulb, and it could be closed or turned on by a switch. When he came to draw this, his symbols looked much like the real thing, so we have a symbol for a light bulb and a switch. But there was a problem. Not everybody used the same symbols in their circuit diagrams. So to avoid confusion, everybody had to agree what the symbols were. Now builders, engineers, and not just electricians can understand circuit diagrams. For instance, when they see this symbol, they know it represents a light sensor.
Now, 3 very common symbols to remember are the symbol for the battery, the symbol for the light, and the symbol for the switch.
Look here. I've got a question asking me to draw a diagram. Draw a circuit diagram in which the switch can be used to turn the motor on and off. You must use these 3 symbols in your diagram: battery, switch, and a motor. Well, I have to use the battery and connect that to the motor, and then go back to the battery.
Well, you've drawn a circuit there, but like this, the motor will always be running. Is that the question?
Well, let's have a look at the question again. It's asking me to draw a circuit diagram in which the switch can be used to turn the motor on and off.
And what did you forget?
The switch.
Putting a switch in the circuit allows you to break the circuit when you want. And when the circuit is broken, the motor is...
not working.
Well done. So put it in then.
Here are 2 different circuits which use the same kind of battery and bulb. Which bulb will be the brightest? I know. We did an experiment in class about this. We found out that the more batteries in a circuit, the brighter the light. And the more bulbs in a circuit, the dimmer the light.
That's right. So which bulb will be the brightest?
Well, both circuits use the same amount of batteries. But one circuit has 1 bulb, bulb A. The other circuit has 2 bulbs, bulbs B and C. So the brightest bulb will be bulb A.
That's right. Excellent. Tick the box. Now it's time for us to fill the memory bank and link together the key things we need to remember. A circuit usually has a battery, a switch, and a component that does something, such as a bulb, a buzzer, or a motor. A circuit is complete when the switch is closed. Electricity travels through a complete circuit. Some materials are conductors of electricity, like metals. Others are electrical insulators, like plastic or wood. Now you and your teacher can go over some of these things, but don't forget, playing with electricity can be very dangerous, so only investigate electricity at school with your teacher. There are also our books, audio tapes and interactive Revisewise website to help you make the most of what you know when you're preparing for your test. The next programme is about forces. these programmes and in our books, audio tapes and on the internet, we're helping you with your Key Stage 2 science tests. This time we're looking at forces. The science test papers often have questions about forces, like this one. Would you read it for us?
The children have some balloons in the classroom. They've been filled with helium. Hilary puts 12 paper clips on the string of her balloon. The balloon stays at the same height above the floor of the classroom when she lets go. Explain why the forces acting on Hilary's balloon with 12 paper clips on the string make it stay at the same height. Well, I know there's questions about forces because it says so, but I need some help sorting it out.
OK, let's remind ourselves what forces are all about and then see if we can answer the question. These are forces at work. See if you can recognise pushes and pulls. Some pulls and pushes are easy to spot. When the man pulls and pushes the trolley, you can see him doing it. But do you think there are any other forces, any other pulls or pushes acting on the trolley? Any ideas? Well, let's have a look at something else which should give you a clue.
You're going to run up, round the right of the person, who's your marker, round the person, back down again, and get your charioteer behind the white line. There's just one thing that we're going to do before you begin. Could you two take your shoes off? And instead of shoes, would you put those on? And instead of shoes, would you put those on?
The children wearing the shoes won the race.
Right, we're going to do it again, but this time you're going to wear the socks and you're going to wear your sand shoes.
Once again, the children wearing the shoes won the race.
What kind of race was it? Was it a fair race? No. Why was it not a fair race?
Because Philip and Louise had to wear socks and they were slipping all the time.
Right. What does that tell me about sand shoes and socks?
It's got grips and socks really don't.
They've got
grips. Shoes have got grips.
Does anybody know what we call that force that's between the shoe and the surface of, say, the ground or wherever you are? Does anybody know a name?
That gripping force between the shoe and the surface has a special name. Do you know what it is?
I know, it's friction. Is that a force then? I thought a force was pushes and pulls. I can't see any pushing or pulling going on there.
Well, you need to think about surfaces. Sometimes we look at some surfaces and they seem to be completely smooth. But if we look closer, using a microscope, we get a different picture. I mean, you'd think an eggshell was pretty smooth, wouldn't you?
Even if something looks perfectly smooth to the naked eye, if you look at it magnified thousands of times under a microscope, the surface is actually covered in tiny bumps. The same goes for the bobsleigh's steel runner. Up close, it's actually quite bumpy. And the ice is scored with fine lines and ridges. When one surface slides across another, the bumps and ridges have to slide past each other. This makes it harder to slip. It causes
friction.
The science team have an experiment that shows friction in action.
Here is an experiment to help you feel how friction works.
Take 2 shoe brushes. Each one represents the surface of an object. So let's say this represents the surface of a table and this represents the surface of a book.
When you put the book on the table,
the bumps of the surface interlock like this.
And when you're trying to push the book on the table,
the surface resists the movements and the bumps are pushing back like this.
Try it yourself and you'll really feel what friction is about.
You can see friction working in lots of places. It can slow down moving things or make it hard to get things moving in the first place.
I get friction now. It's a force that tries to stop things moving.
Yeah, that's right. And there's something else that slows down moving things. It's air. The force of air pushing back on moving things is called air resistance.
When I run with the card, it is really hard. I can really feel the air pushing against me. When he ran without the card, it took him 8 seconds, and when he ran with the card, it took him 10. The card slowed him down.
Let's go back to the supermarket trolley. When it's pushed, there's more than the man's push force at work. There's a bit of air resistance pushing back. And there's the friction between the wheels and the ground. Can you think of any other force at work?
I know, it's gravity.
Let's get the science team to remind us a bit about gravity.
Gravity is an invisible force between an object and the Earth. It pulls on everything towards the center of the Earth. Because gravity is invisible, some people find it hard to think about.
If I let this ruler go, you could see that it had fallen to the ground. But really, there is an invisible force named gravity that had pulled it down to the ground.
Yes, gravity is a bit like an elastic band. Let's say that this box represents the Earth. If I let go of this ruler, it gets pulled back to the center of the box.
So whenever you are thinking about gravity, try and imagine an invisible elastic band attached to everything on the Earth and the center of the Earth. Wherever you are on the Earth, you will not fall off the center of the Earth.
But there's one thing you've got to remember. Gravity isn't exactly like an elastic band. Because as you go miles and miles away from the Earth, the force from gravity gets weaker and weaker.
So, gravity is the force that pulls everything towards the centre of the Earth, wherever you are on its surface. In one test question about gravity, there was this drawing of the Earth, as if you were looking at it from a long way away. You had to draw where the plumb line being held by the person would fall. Now, a lot of children drew the line this way, down the page. What they should have done was to imagine they were on the drawing of the Earth, and the plumb line should be drawn towards the centre of the drawing of the Earth.
Oh, I got that, but there's something I still have a bit of a problem with. If everything gets pulled towards the centre of the Earth, why doesn't it keep on going? Why doesn't everything go through the floor?
OK, well, to explain that, I'm going to give you this balloon. Now, hold it between your hands like that, yep. Now, see if you can change the shape of the balloon. Now, to do that, are you pushing with one hand or both hands?
Both hands.
You're definitely pushing from each side to change the shape of the balloon.
Yes.
OK. Put it flat on the desk. Now, push with that hand on top. Now, the balloon's changed shape again, and before we saw that you had to push from each side to change the shape of the balloon. Now, your hand is pushing from one side. What do you think might be pushing from the other side?
The table. The table's pushing from the other side.
Fantastic. Here's another explanation.
See these books on the table? Don't look like they're doing much. But the weight of the books is pushing down on the table. And that's not all. The table's also pushing back on the books. Imagine Imagine what would happen if it didn't. Even these comfy cushions can push back on me. Watch what happens as I sit down. Let's look at that again. At first, my weight is a bigger force than the upward force of the cushion springs, so I go down. But the more squash the springs get, the more they push back. Eventually, the force pushing back equals my weight. The forces in each direction balance, and I stay put.
When the trolley is at rest, the force of the gravity and the force of the floor pushing back are both acting on it. And when it moves, gravity and the force of the floor are still acting on it, but you also have the push or pull of the person who is making the trolley move, the friction between the wheels and the floor, and the air resistance. Now, we've just learned that solid surfaces can push back on things, but what about water?
Can water push back too?
Well, let's pop this balloon in the tank. Now, you push down on the balloon, and what can you feel?
The water pushing back on me.
Excellent, the water is pushing back. Now, let the balloon float. Now, are there any forces, pushes or pulls on the balloon?
Well, everything gets pulled towards the centre of the Earth. So, there's a pull from gravity down the balloon, and there's a pushback from the water.
Exactly. The pushback from the water can also be called upthrust. And if it was a battle of the forces?
Well, if it was a battle of forces, gravity would be on the down team, and upthrust would be on the up team. But the forces are the same size, but in opposite directions, so the balloon will stay where it is. It won't go up or it won't go down.
Brilliant. Now, what about the helium balloon in the test question? Can you tell me about the battle of the forces there?
Well, they say helium's balloon stayed at the same height when she let go. But there must be a pull from gravity on the balloon. But it isn't moving, so there must be something pushing or holding it up. And there's only one thing it can be. It's the upthrust from the air. And in the battle of forces, the down team is matched by the up team, so the balloon isn't going anywhere. It's staying where it is.
Brilliant. Now, what would happen if we added an extra paperclip to the string on the balloon?
Well, the force of gravity will get bigger, and the down team will get bigger than the up team. So the balloon will go down until something stops it, like the floor.
Fantastic. So now it's time to check what keywords we've got to put in the memory bank. A force is a push or a pull. Among the push forces are air resistance, upthrust in water and in air, and friction, a pushing back force between surfaces. Gravity is a pull towards the centre of the Earth. Now, you and your teacher can go over all of these things at school, and don't forget you can always wind the tape back and look at bits of the programme again. There are also books, audio tapes, and our Revisewise website to help you prepare for your test. So, we'll let you get on with your test, and let you get on with your revision. The next programme is about forces and measurement. In these programmes and in our books, audio tapes and on the internet, we're helping you with your Key Stage 2 science tests. This time we're looking at forces and measurement. Here's a question about forces and measurement. Could you read it to us?
Ellen and Michael investigated how 4 different objects stretch 4 identical elastic bands. Which object was the heaviest?
Here the science team are doing exactly that, hanging the different objects on elastic bands to see how the bands will stretch.
Well, I can do this one, because the heaviest object would make the band stretch the most. And here, the stone is making the band stretch the most. So, the stone is the heaviest. Oh, but the next bit's more difficult.
Well, don't worry, we've still got to write down the answer to the first question before we go on.
Oh, yeah.
OK, so what's the problem now?
They used a force meter to measure the weight of an object in newtons. I can measure length and volume, but how do you use a force meter? And I thought Newton was a scientist.
OK, well, measuring forces is just like other types of measuring. Let's get the science team to help us with it.
I've got a force meter here. It's got a spring in it. It stretches when something pulls on it. With it, I can measure different strength forces. I can measure pulls or pushes in a unit called newtons, so you can see it's marked here, newtons. I can measure a small pull. I put my little finger here, and that's quite small, 2 newtons. I can also measure a bigger pull, let's say 10 newtons.
We've got lots of force meters here. They all are different. They all have a different scale on them. This one measures 20 newtons, and this one measures 50 newtons.
The biggest force this one can measure is 1 newton, and this one is 10 newtons.
So some newton meters are better for measuring a smaller force, and some newton meters are better for measuring a larger force.
There's a great game you can play with a newton meter. Fieldy, close your eyes and pull a 20 newton. Have I got it? No, you pull 10 newton. Try and pull a 5 newton. Have I got it? Yes, you have. It's great fun. Try it yourself. The more you play, the better you get at guessing.
So now you know how easy it is to use a force meter or newton meter to measure the size of different pull forces.
Yeah, no problem. So newtons are what you measure force in?
Yes. It's just a name for the unit, like meters measure length. Now, what's inside a force meter?
It's a spring, isn't it?
In the test, they might ask you about force meters, but they might also ask you about springs and elastics. There is only one thing you need to know about springs. Springs will always try to go back to their original shape. So if you pull on a spring and stretch it, it will pull back on you. And the more you stretch it, the more it pulls back. And if you squash it up, it will push back on you. And the more you squash it, the more it pushes back. Elastic things are different. They don't push back on you if you squash them up, but they do pull back if you pull on them, which is just as well for bungee jumpers. Now, have a look at Stella from Science in Action using force meters to measure big friction forces.
I can just lift the crate. So if I could get something smoother underneath it, that would make the friction less and I wouldn't have to use so much force to move it. But what sort of thing can I put under it? I know what might help. This is my sledge. Meant to slide, isn't it? Ah. But what about this rubber on the runners? Could be a problem. We'll see. To move this, I need to apply a force of 220 newtons. Can my sledge improve on that? Oh, this made things worse. 320 newtons. The rubber on the floor has increased the frictional force. I'm going to have to try some different materials on my sledge runners. I've organised an experiment to find out which material has the least friction force when it moves over the aircraft floor. I'll use this block to represent the sledge runner, weights to represent the crate, and this is the floor. Now first, I'll attach in turn each of these materials. And then I'll attach a forceometer onto the block and try and pull it across the flooring. And the forceometer will tell me how much force is needed to be greater than the friction force. Polythene. Shiny. Sandpaper. It's a bit rough. But then, if I put sand under the block, might work. Baking tray. This is non-stick Teflon. All in the cause of science. So some obviously did better than others. Sandpaper, made up of all those tiny grains, 68 newtons. Wood, 42. Polythene, even though it was very shiny, still needed 36 newtons. But the material with the least frictional force of those I tried was Teflon, 30 newtons. So, all I have to do is put Teflon on my sledge runners, and away I go. Have I got any more baking trays?
Force meters can also be used to measure other forces, like magnetic forces. Listen to what Stella has to say.
Look at this. Now, 2,000 years ago, the ancient Greeks found that some stones, like this, could do strange things. They could attract each other and iron. Now, these stones were called lodestones. And they also found that if you stroked a nail or similar metal along the stone, then these strange attractive powers could be passed on to the metal. Lots of these stones were found near a Greek town called Magnesia, so they call the lodestone's attractive force magnetism. Now, some materials are magnetic, but you can't tell just from looking at them. For example, some metals are magnetic, but many aren't. So you have to test them to find out. These 6 magnets are suspended. Move them closer together. Why? Well, the ends of the magnets are called poles, one the North Pole and the other the South Pole. Bring 2 like poles together, both south, both north, and the magnetic force pushes them apart. They repel. But bring 2 different poles together, one north, one south, and the magnetic force pulls them together. They attract. A magnet doesn't have to be touching whatever it's attracting, like this paperclip. The force of the magnet can be sensed all around the magnet, and this space of attraction is called the magnetic field.
Oh, I remember now. Magnets pull some metals towards them. There's a magnetic force.
That's right. Now here we've got 2 magnets. We have to be careful because they're very heavy and they're very strong. Now how much force do you think it would take to pull them apart?
I don't know.
What do you think the force would be in newtons? Well, how can we measure it?
Use a force meter.
That's right. Now you take that force meter. We'll hook the magnets on. I'll hold this end and hold onto the magnets in case they fly off. You try and pull them apart.
Oh, that's as far as I can go.
OK, well, that was 40 newtons and they didn't come apart. So it would take a force of more than 40 newtons to pull these magnets apart. Magnets can be pretty strong, can't they? So far, we've only used our force meters to measure horizontal pulls. We can also use them to measure the pull down on things due to gravity. Here's the science team.
5 newtons. 0.3 newtons. Not 0.4 newtons.
We measured the brick and the scissors in the air and the water.
0.3 newtons.
You can see in this table that the reading in water is less than the air.
If I push up on this brick, the reading on the force meter is less than if I don't push up. So the only way the reading in water is less is because the water is pushing up.
And what do we call that push up from the water?
Upthrust.
Yeah, great. All through this unit, we've talked about using force meters, but what about making one? A member of the science team is telling us how.
You get a piece of wood so it is about 15 centimetres long. Then you get a cup hook and attach it to the piece of wood. Then you get a piece of plastic piping about 4 centimetres long and attach it to the piece of wood. Then you get 2 elastic bands, attach it to the pipe and attach it to the cup hook like this. Then you get a 100-gram weight or an apple, which is about the same, to make your calibrations. Now you can measure in pushes and pulls.
Well, I think you know pretty much everything there is to know about force meters now. So let's have a go at the question.
Okay. They use a force meter to measure the weight of objects in newtons. Why does the force meter contain a spring? Because the spring is shiny, metal, stretchy, or strong. Oh, yeah, that's easy. Stretchy.
Take the box. So now it's time to check what keywords we've got to put in the memory bank. A force is a push or a pull. Springs can push back when you push them and pull back when you pull them. Elastics can only pull back when you pull them. Magnets can push away other magnets and pull magnetic materials and other magnets. A force is measured in newtons. Newtons are the units on the force meters or Newton meters. Force meters or Newton meters measure the size of forces. Now you and your teacher can go over some of these things at school. Don't forget you can always wind the tape back and look at bits of the programme again. There are also our books, audio tapes and interactive Revisewise website to help you make the most of what you know when you're preparing for your test. The next programme is about light. In these programmes and in our books, audio tapes and on the internet, we're helping you with your Key Stage 2 science tests. This time we're looking at light.
Tim and Sue have a torch and a shadow puppet. What does the light from the torch shine on? Tick 2 boxes. The front of the puppet, the back of the puppet, the shadow of the puppet, or the screen. I'm not sure about the next part of the question. Explain how a shadow is formed. I don't know how a shadow is formed. They're just there. You get them when the sun comes out.
So you want to check up on some ideas about light, do you?
That's right.
Well, OK, first question. Can you see in the dark?
Not very well. I can sort of make out vague shapes.
Well, Stella from Science in Action has been investigating.
My dark lab seems the perfect place to start. Maybe Boffin here can help. So why can I see her eyes in the dark? What else can I see in the dark? Shiny things? White things? Ah, but it's not really dark though, is it? My torch is on. Interesting. In the dark, I can't see anything at all.
So if there's no light, if it's completely dark, I won't be able to see?
That's right. If you can see anything, even just vague shapes, then there must be a little bit of light around. Next question. How do we hear?
We hear when sound goes into our ears, in that hole. But why are you asking me about sound? We're talking about light.
We are. You told me that your ear had a hole to let sounds in. Well, your eyes have a sort of hole to let light in.
Yuck, a hole in my eye? Where?
Well, look in my eye. That black bit in the middle, the pupil, now that's the hole where the light goes into my eye. Just as you can only hear when sound goes into your ear, you can only see when light goes into your eye.
For us to be able to see anything, light has to bounce off what we're looking at, in this case, the dinosaur. The eye is a ball with a hole at the front, the pupil, where the light goes in. On the inside of the pupil is a lens which focuses the light on the surface at the back of the eyeball. This surface is called the retina and is made of special cells that react to the light and send messages to our brains, and so we see. If light gets too bright, the iris, that's the coloured part, can make the hole smaller and so let in less light.
Have a look at this. Now turn it on. Can you see the light from the torch?
Of course.
OK, now I want you to draw me a line on this diagram to show what happened to the light from the torch so that you could see it. Well done. You've got the light going the right way into the eye, but when you're showing how light travels, it's important to show the whole of the light's journey and also to draw it using straight lines, because light travels in a straight line. Here, have another go. Well done. You've shown that the light started from the torch, that it went all the way into the eye, and that it travelled in a straight line. Now, have a look at this box. It's got something inside it. Now, do you think you're going to be able to see what it is?
I just looked for that hole.
Well, see what the science team discovered when they tried to look inside the box.
I can't see a thing, can you? No, neither can I. It's pitch black. Give it to me. No, I can't see anything either.
Is that really right? They couldn't see a thing?
Try it.
They're right. I can't see anything. I get in now. There was no light to come into my eye, so that's why I couldn't see.
Good. See what a difference it makes if you let a bit of light in. Watch again.
Let me turn the torch on. I can see now. There are some keys in there. Let me have a turn. Yes, I can see them. Now that the light is shining on the keys, I can see them. It must mean that we can only see the keys when the light hits them. Here are the keys. Now that the light is shining on the keys from all around, we can see them really clearly.
When the box is closed, now we'll just open it up so we can have a look. The light comes through here and then hits the object which is in the box. In this case, it's some keys. And then it's reflected by the object and goes up here and into your eye, which is watching through here. Now, this is how we see everything around us.
In the dark, you can't see things. You need a light source. A lamp, a candle, or the sun before you can see anything. This is because we only see things around us when light is reflected from them into our eyes. light from the light source travels to an object and is reflected into our eyes. This is how we see the object. Everything around us reflects light. But some shiny things, water, metal, glass, and mirrors, reflect all the light. If a surface is smooth and flat, you can see yourself clearly. But mirrors turn you around from side to side. When you hold up your left hand in a mirror, your reflection makes it seem as if you are holding up your right hand. Just like your writing looks different if you hold it up to a mirror.
So everything reflects light, but mirrors and other flat, shiny surfaces do it really well. Watch the science team experimenting with light and mirrors.
Mirrors are really good fun to play with. They can help you to understand how light works.
One good game is to try and hit a target using a torch and a mirror.
The light goes from the torch to the mirror. It is then reflected by the mirror to hit the target.
In the same way, the person holding the light could see the target because the light of the room is reflected by the target, goes to the mirror, then is reflected by the mirror, then enters the person's eyes.
Another good game is to experiment with two mirrors and find out what you can see.
For example, if I put a mirror in front of me and Jackie puts a mirror behind me, I should be able to see the back of my head.
That is because the light around the room is reflected by his neck onto the mirror that I am holding, reflected onto his mirror and into his eye.
I see. They use mirrors to make light bounce off in another direction.
That's it.
You know, we've been talking a lot about light, but I still haven't worked out how to explain how shadows are formed.
OK, keep watching.
300 lux. $500 lux. $500 lux.
We did this experiment to see how transparent materials are. Some block the light like these, and some let the light through like these. And some let the light through, but not completely, like these.
So different materials let different amounts of light through, but how were the shadows formed? I still don't know how to explain.
Well, try thinking about what happened to the light. The trees block the sunlight. So does the bee. Look at this shadow puppet. The puppet blocks the light from the lamp. And so does the hat. And what about this sundial?
I see. You get shadows when the light is blocked. That's why shadows are dark. No light can get there.
So now, do you think you can answer the question in your test paper?
Tim and Sue have a torch and a shadow puppet. What does the light from the torch shine on? Tick 2 boxes. The front of the puppet, the back of the puppet, the shadow of the puppet, or the screen? Let's see. The front of the puppet looks like it has light shining on it, so I think I'll have to tick that one. I can't see the back of the puppet, but I'm pretty sure it hasn't got any light shining on it, so I won't tick that one. The shadow of the puppet looks dark, so I don't think it has any light shining on it, so I won't tick that one. But the screen does look like it has light shining on it, so I'll tick that one. I'll tick the front of the puppet and the screen.
Very good. And what about the next part of the question?
Explain how a shadow is formed. You get shadows when the light is blocked. So that's what I need to write down. The shadow is formed because the light is blocked.
Well done. The thing you've got to remember is that light travels in a straight line and won't bend around an object. So what happens to the shadow as an object goes further away from the light source?
It gets smaller.
That's it. There's a relationship here. The longer the distance between the light source and the object, the shorter the shadow on the screen. Why do you think we get a bigger shadow when the object is closer to the light source?
Almost all of the light is blocked off. Hardly any of the light can get past the object.
Good. You know you said that the shadow got shorter as the object got further away from the light source. Well, do you think that it would eventually disappear?
No, there's always a shadow there. It doesn't disappear.
You're right. What can you tell me about the height of the shadow now?
Just a bit more than the height of the object.
That's right. The shadow will always be at least the height of the object. Let's finish that question then.
The height of the puppet is at 20 centimetres. The graph below shows the height of the shadow on the screen changed when the puppet was moved away from the torch. Well, the graph makes sense. You can see the height of the shadow getting less. But what's next? Continue the line graph to show what the height of the shadow will be when the puppet is at 250 centimetres and 300 centimetres from the torch. OK, I know the height gets less, so the line will go on down.
Whoa, not so fast. Now, if you put in that line, what would be the height of the shadow here?
Oh, 0 centimetres. But the shadow can't be less than the height of the object. How big was the puppet? 20 centimetres. So my line mustn't go beneath 20 centimetres.
Don't worry if your test paper looks a bit messy, because you won't lose any marks for it. So now it's time to check what keywords we've got to put in the memory bank. Light comes from a light source, like the sun or a light bulb. Light is needed to see. If light goes straight into our eyes, we can see it. Light is also reflected by object surfaces and then goes into our eyes, and that's how we can see objects. Light can pass through some materials and is blocked by other materials to form shadows. Now you can go over all this at school by winding the tape back and looking at bits of the programme again. There are also books, audio tapes, and our Revisewise website to help you prepare for your test. The next programme is about sound. In these programmes and in our books, audio tapes and on the internet, we're helping you with your Key Stage 2 science tests. This time we're looking at sound. Here's a question about sound. Can you read it for us?
Anne clamped a ruler to a desk. She pressed down on the ruler and then let it go. Why was there a sound when Anne let go of the ruler? The ruler made a noise.
Hang on. That's not a very scientific answer. You need to explain why. Let's see if we can help you sort out your thoughts. There are lots of different sounds, but they all have something in common. They're all made when objects do something.
Is it when they do that?
You're on the right lines. Watch this and see if you can pick up the words you should use to explain how sounds are made.
1, 2, 1, 2, 3, 4. I wish I could play the drums better, but I can show you how sounds are made. Watch this. I'm just going to put a bit of rice on the drum like that. Now watch this. So what's making the rice jump after I've stopped banging? I can feel the vibration there. And the same goes for the cymbal. You can see the vibration, especially at the edges. And you can see it better when it's slowed down. And speed it up. When the vibration stops, so does the sound. So sound is all about vibrations.
And that's how I should explain why there was a sound when Anna let go of the ruler. I should say the ruler was vibrating.
That's it.
OK, on to the next part. What did the sound travel through to reach Jack's ears? That's a bit of an odd question. There's nothing between the vibrating ruler and Jack's ears. So I suppose I should write the word nothing as my answer.
Well, just hang on before you do that. Let's have a look.
We can see the bell is ringing as well as hear it. This close, the sound is quite loud. As we move away, the sound of the alarm gets quieter. So the distance affects how loud we hear the sound. As we move around the clock, we can still hear the alarm. So the sound travels out from the ringing bell in all directions. The vibration is moving through the air to reach our ears. Sound always needs something to move through. We can show this if we put the clock inside this special jar. But first, the ringing becomes quieter because the clock is now inside the jar. The air inside the jar can be pumped out. The gauge shows that with each pump, more and more air is being removed. Most of the air has now been pumped out. The bell is still ringing, but we can't hear it. As the air is allowed back in, the bell can be heard once again. This shows that sound vibrations need something to travel through. Here, it's air.
For you to hear sounds, there must always be something for the vibrations to travel through, even if it's just air. The science team experimented.
It is hard to believe that vibrations travel through the air because we cannot see the air vibrating, but we are going to prove that vibrations do travel through the air. Firstly, I'm going to hit the bottom of the drum. The skin at the bottom of the drum starts to vibrate. The vibrations travel through the drum to the top skin of the drum to make that vibrate. So if the vibrations travel through the air and reach the paper, that will make the rice jump. So if the rice jumps, that proves that vibrations travel through the air. Let's see. So there you are. Sound vibrations travel through the air.
You convinced me. Sound travel through air. That's the answer to the question. Air. That's what the sound travelled through to reach Jack's ears.
Well done. And it's not just air that sound can travel through. It can travel through all sorts of materials.
When I swing the fork to hit the table like this, I can hear the sound very loudly because it is travelling up the string.
So sound travels through air, sound travels through string. What about water? Let's try it with this bell. Yeah, it's out of water, and as I lower it in... It sounds a bit quieter from out here. But what happens if you try listening under the water? I'll use this microphone. It can be my ears. So there's the bell. Lower it under the water. Put the microphone. No doubt about that. Sound travels very well underwater. I wonder what music sounds like. Let's try it. I've got this here, my special underwater loudspeaker. So if I have a bit of music, there, I'll lower it into the water, and then the microphone. Now you can hear it. Now, which note's the clearest? The high or the low ones? So there we are. Some good vibrations underwater.
Sound doesn't only travel through air, it can travel through anything. For example, if you tap your elbow like that, you will hear a small sound. But if you tap your elbow like this, the sound of the tapping will be travelling up your bone into your ear. Because sound travels better in bone than in the air, the sound is louder.
That's true.
They're right. The tapping sounds a lot louder when you can hear it through the bone.
Yes. Some materials, like bone or string, are good at passing on the vibrations from sounds. Other materials are not so good at passing on the vibrations. They absorb the sound. When you want to cut down the noise, materials like that can be very useful. You can do tests to find out how much different materials absorb sound. Have a look.
I like that tapping machine. I don't suppose you've got one of those. I certainly haven't. But here's an experiment you can do to find out how well different materials cut out noise. First of all, you need something that's going to make a bit of a noise. And I've got a tin here with 3 pieces of wood. And I'm going to pop a handful of marbles in. Like that, and pop the lid on the top so that I don't lose my marbles. Now I'm going to roll it down a slope. And listen out for the noise. Hear the noise there? Now cover the tin with some material. Right, I got one already covered with some cotton wool. And make sure you've got the same number of marbles in the tin. And listen out for the noise this time. Oh, that was a little bit quieter. You can try different kinds of materials to see which one works the best. For example, here I've got some felt, corduroy, carpet and lino even, to see which one of those works the best. But see if you can make it a fair test. For example, is the size of the piece of material important? The weight of it? And what about the way that I rolled it down? Perhaps I should have been a little bit more careful to make it a fair test. And also, what about the noise? I measured it with my ear. Perhaps you can find a better way of measuring it. In fact, this is just my suggestion for a test. I'm sure you can think of a better one.
We've heard a lot of sounds already. Some of the sounds were high and some were low. Their pitch was different.
Yes, I remember doing some investigations about pitch, how you could change the sound to make it higher or lower.
Well, watch this film and see if you can spot 3 different ways to make the pitch change.
On this board is a string which is fixed at one end and attached to some weights at the other. Listen to the sound the string makes when it's plucked. We can see that the string is vibrating to produce the sound. Now listen again after an extra weight is added. The string now produces a sound with a higher pitch. The weights pull the string so it becomes tighter and so vibrates faster when it's plucked. There are other ways of affecting the sound pitch of a string. These strings all have different lengths. The vibrating length of string is between the black strips of wood. The weight on each string is the same. The longer strings produce a lower pitch sound than the shorter strings. So the shorter length strings are vibrating faster than the longer lengths. All these strings are the same length and have the same weight attached. The difference this time is their thickness. The strings get thicker as we move across the board. The thinner strings produce a higher pitch sound than the thicker strings. This is because the thicker strings are heavier and don't vibrate as quickly as the thinner strings.
I've spotted the 3 ways to make the pitch change. You can make the string tighter or looser, you can change the length of the string, and you can change the thickness of the string.
Well spotted. The tension, that's the word for tightness, the length and the thickness all made a difference to the pitch of the sound. Did you notice that each time only one thing was changed to make sure it was a fair test, and that the effect was due only to that one thing they changed? For example, when the tension was changed, the length and the thickness stayed the same. Now, here's a quiz for you. I'll start a sentence and you finish it with either the higher the pitch or the lower the pitch.
Okay.
The tighter the string.
The higher the pitch.
The thicker the string.
The lower the pitch.
The longer the string.
The lower the pitch.
The thinner the string.
The higher the pitch.
The looser the string.
The lower the pitch.
The shorter the string.
The higher the pitch.
Well done. I couldn't catch you out. Now let's have a look at the next part of the question.
Anne shortened the length of the ruler sticking out from the desk. She let go of the ruler from the same position as before. Describe how the sound was different. Well, if she shortened the length of the ruler, it'd be like shortening the string, so the pitch would be higher. Hang on, let me check. Yep, I was right.
Now, there's something else other than pitch that we can change on sounds. We can make them louder or quieter. We can change the loudness. If we pluck or hit things hard, we make big vibrations, and big vibrations mean loud noises. Have a look at the last part of your question now.
Anne fixed the pen to the end of the ruler. Jack moved towards the table with a piece of paper touching the pen. Jack moved steadily and Anne plucked the ruler once. Look at the pattern the pen made. What happened to the loudness of the sound between A and B? Well, the vibrations here are big, so that means a loud sound. And the vibrations here are smaller, so it's quiet. And so from A to B, it got quieter. What's next?
What does the pattern tell you about the sound at point C?
That's easy. There was no sound, and I can explain that.
Go on then.
There's no sound because there the ruler is still. It isn't vibrating. No vibrations means no sound.
That's it. Sorted. So now it's time to check what keywords we've got to put in the memory bank. Sound is made when an object vibrates. Sound can only travel through materials. It cannot travel through a vacuum. You can change a sound's pitch, how high or low a sound is. You can change a sound's loudness, how loud or quiet a sound is. Now you can go over all this at school by winding the tape back and looking at bits of the programme again. There are also books, audio tapes and our Revisewise website to help you prepare for your test. The next programme is about Earth and beyond. In these programmes and in our books, audio tapes and on the internet, we're helping you with your Key Stage 2 science tests. This time we're looking at Earth and beyond.
The diagram shows the Sun, Earth and Moon. Write Sun, Moon and Earth into correct boxes on the diagram. 2 orbits are shown. Write the time taken in days for each orbit. I can always get in the muddle of this. I can never remember if the Earth's doing an orbit or if it's spinning, or is it doing both?
OK. Well, let's take things step by step. The Earth orbits the Sun.
You know, I'm not sure what orbiting means.
It means going round. The Earth orbits the Sun. It goes round the Sun. The Earth is millions of miles away from the Sun, so it takes a pretty long time to orbit the Sun. In fact, it takes 1 whole year, that's 365 days. But the Earth doesn't just do that. Sarah from the Experimenter went to the Greenwich Royal Observatory to find out more.
You can see the stars moving, but sooner or later, you see there's going to be a change. The sky gets brighter and brighter because the sun's coming up. And as the sun comes up, of course, the stars disappear or seem to disappear because the sun's too bright for them. Right across the sky, that sun will travel, starting, of course, in the east when it rises in the morning. Then it reaches, as it is now, the south point. Then it's now going down and down towards the horizon. Eventually, it gets darker and darker, and the stars come back again. Now, it can't possibly be the case that the sun and the stars are moving together. But something's moving, and if it isn't them, it must be us. The Earth under our feet is actually spinning.
Well, I do believe you, but I can't quite imagine it, though.
Well,
Harry took me to where he had a model of planets moving round the sun.
This shows the actual spin of the Earth. You'll remember that the Earth goes round the sun, and it takes 1 year exactly to do that. But while it's doing that, it is also spinning on its axis. And that, of course, is a day and a night as it spins round.
So, we have days and nights because the Earth's spinning around?
Yes, exactly.
How do we go from day to night? It's nighttime in part of the world, but it's daytime in other parts. Britain faces the sun. It's daytime. But the other side of the world is in darkness. In Australia, it's the middle of the night. But the Earth rotates. As it rotates, parts of the Earth that were facing the sun turn away from it. The Earth rotates one complete turn every 24 hours, so day is followed by night, is followed by day.
And it's also because the Earth is spinning that the sun seems to be going across the sky during the day.
Now, if we use the little man, in the early morning from the British Isles, he has to look down towards the eastern horizon to see the sun. By midday, he must turn round and look upwards. Then by the evening, he has to swivel right round and look down towards the western horizon to see the sun setting. The Earth has spun right round, and that's the explanation for the sun seeming to go across the sky. The Earth has spun.
The Earth spins about its axis and it orbits the sun. It does both things at the same time. It takes 1 year to orbit the sun and 1 day to do one spin. So it spins 365 times a year. There's something else you need to think about. The moon. The moon goes round the Earth. It orbits the Earth.
Now, Michael is the Earth, Verdina is the sun, and Zara is the moon. We're going to begin with the sun. So come on, sun, into position. Now the Earth into position. The Earth moves around the sun. It takes the Earth 365 days, which is a year, to make that journey. Now let's have the moon in position. The moon goes around the Earth. It takes it about a month to make that journey. Now let's all move together. And this is what happens in space.
They were just showing the orbit of the Earth and the Moon. It takes the Moon 28 days to orbit the Earth, and that's why it seems to us that the Moon changes shape.
If you look at the Moon on different days, you will see it seems to have a different shape. Sometimes you can hardly see it at all. Other times it looks like a back-to-front letter C, or half a circle, or a nearly blown-up ball, or a complete circle. Then it looks like a nearly blown-up ball again, then half a circle, then a letter C, and then once more you can hardly see it. It takes about 28 days to do all this. Then it starts all over again. But the Moon doesn't actually change shape each night. It's really that on Earth we keep getting a different view of the part of the Moon the Sun has lit up. That's why it seems to change shape. If you could stand and watch the Moon in the night sky for a whole month, this is what you would see.
What about that test question then?
The diagram shows the Sun, Earth and Moon. Write Sun, Moon and Earth into correct boxes on the diagram. 2 orbits are shown. Write the time taken in days for each orbit. OK, we said the Earth orbits the Sun and the Moon orbits the Earth. So that must be the Earth. That must be the Moon. And that must be the Sun.
Yes.
And it takes 1 year, or 365 days, for the Earth to orbit the Sun. And it takes 28 days for the Moon to orbit the Earth.
Great!
I've got a question here about shadows, and I'm not sure how to answer it.
Well, read it out.
Debbie measured the length of a shadow at different times of the day. She recorded her results. And then there's a table here which shows her results. And then it says, tick the box below which shows the length of the shadow at 2 p.m. 81 centimetres, 90 centimetres, 105 centimetres, 110 centimetres. How am I supposed to guess that?
Well, have you ever noticed what happens to shadows during the day when the sun is out? Do you know why this happens?
No.
Well, we already know that the Earth is spinning, and each morning the sun seems to rise and then travel across the sky until it sets again in the evening.
What's that got to do with shadows?
Well, XP from the experimenter wanted to find out exactly the same thing.
Would you like to be the sun this time?
I'd love to be the sun.
Right, there we are, you have that.
Right.
Now,
this is the sun.
That's the sun.
Right, this is the sun.
Now, what I've got here is a hoop that shows where the sun will be at different times of the day. You see, the sun moves in a regular pattern across the sky. It appears to move across the sky. So we can always tell where the sun's going to be. This is where it's going to be at 6 o'clock in the morning.
Yes.
This is where it's going to be at 10 o'clock. At 12 o'clock midday, it's there. 2 o'clock in the afternoon, it's here. And on to 6 o'clock in the afternoon and 8 o'clock.
Right.
Now, what I've got here is a little tower block.
Oh, yes.
And we'll see how the shadow changes during the day. Now, what I want you to do is to hold the torch at the 6 o'clock position.
Right.
And I'll draw the shadow on here. Like that. Now, I'll put a 6 on there so you remember.
Right.
And now, if you move it up to 10...
10, right.
Right. And I'll draw the shadow in again. Can you see how it's changed?
Oh, yes. It's a lot shorter.
That's right. Now, if you move it on to 12...
Midday.
Midday. And there we are. You see it's very short now. And now, if we go on to the afternoon at 4 o'clock, and I'll have to come round here.
Right.
There's the shadow. Ah. There, that's the 4 o'clock one. And let's do one more. 6 o'clock down there. And now we've got another long shadow over this side. It's the 6 o'clock shadow.
I see. That's amazing.
Yeah. Now you can see that the length and direction of the shadows changes.
Well, I understand now. The sun was high and high in the sky until midday, and then lower and lower till sundown. And the higher the sun, the shorter the shadow.
Yes, and remember, the changes in the shadow are all down to the spinning of the Earth. Even though it looks to us as if the sun is moving across the sky in an arc, in reality it's the Earth which is spinning. Anyway, now do you think you can answer your question?
Yes, no problem. The shadow at 2 p.m. is bigger than the one at 1 p.m, but smaller than the one at 3 p.m. So it has to be bigger than 80 centimetres, but smaller than 108. So it can't be 110 centimetres. OK, so now I have to choose between 81 centimetres, 90 centimetres and 105 centimetres. On the table, the shadow is at its smallest at 1 p.m. So 1 hour after 1, it will be about the same size as 1 hour before 1. So the answer should be 90 centimetres. Well, there's something that's been bothering me. On this table, it said that the shadow is at its shortest at 1 p.m. I thought it was always 12.
Well, that's because we change our clock in this country in the summer months. The sun can be at its highest at 1 or at 12, depending on whether we're in the summer months or the winter months. So now it's time to check what keywords we've got to put in the memory bank. The moon orbits the Earth in 28 days. The Earth orbits the sun in 365 days. The Earth spins on its axis once in 24 hours. In the half of the Earth which faces the sun, it's daytime, and in the half of the Earth which is away from the sun, it is nighttime. The Earth spinning on its axis makes it look as if the sun moves across the sky in an arc. Because of this, shadows change. They become smaller and then bigger and change their position during daylight. And don't forget, the shadows are shortest when the sun is highest in the sky. Now you can go over all this at school by winding the tape back and looking at bits of the programme again. There are also books, audio tapes and our Revisewise website to help you prepare for your test. So, I'll let you get on with your test and you get on with your television revision.